Hello everybody, and a warm welcome from my side to this pre-course in optics by the Abbe School of Photonics, Friedrich Schiller University Jena in Germany. So in this series of lectures, I will present to you a tour through the basic phenomena of optics, mostly by experiments, and I will explain some of the theory to you. So you can access the lecture material on this website, and I want to start first by a big thank you to my colleague Richard Kovacic, who basically laid the foundations of this lecture and gave me his lecture material to build upon. So what are we going to learn? Well, first we start with the first course on the basics of optics, geometrical optics, interferometry, the phenomenon of diffraction, and we'll end these lectures with polarization. So the aim is that you are remembered and reminded of some basic knowledge, and of course you might also learn something new about optics. So if you want to read more details, I can recommend this book by Hecht called Optics, and it is published by Addison Wesley 2002. Of course, the book contains a lot more material than we are going to be able to cover in this lecture series. So let's start right away with geometrical optics. We're starting with the laws of reflection and refraction. Then we go into Fermat's principle in optics, continuous geometrical optical imaging. Then we are dealing very shortly with aperture stops, pupils, and windows, a little bit of aberration theory, and then end this first lecture on optical instruments. So what is geometrical optics? Well, it is an approximation where you are imagining that light travels by rays. It travels along straight lines, which are called light rays. And if you already know a slightly refined picture, which is sort of the wave picture of light, you can imagine that such a light ray is sort of the approximation perpendicular to the wave fronts of the wave optics view of optics. So what are the assumptions? Well, propagation in straight path in a homogeneous medium is called a light ray, and more precisely it is the direction of flow of energy, so in other words the direction of the pointing vector. Then these light rays of course follow the laws of reflection and refraction at interfaces, so they get bent at these interfaces. Then there's a principle of reversibility, which means you can trace all these rays backwards and would still get a valid view of physics in geometrical optics. And there's the principle of superpositions, which means you can sort of get the picture of what many rays do by superimposing them. Here you see such a simple ray diagram where a light ray going this way travels through one medium, hits an interface, as shown here, where it transitions from one medium characterized by the refractive index N1, or also called index of refraction, into a second index of refraction, a second material N2. And if these numbers N1 and N2 differ, then this direction of the light ray will change inside the medium. So here we see, for example, the situation going from air into water. So the light ray gets bent towards the normal of that surface, the interface surface. And of course, in addition to that transmitted ray, we also have a reflected ray going this way. And of course, the laws of reflection tell you that the angle of incidence towards the surface normal is equal to, on the opposite side, the angle that it is leaving towards that normal. So that's the law of reflection. We will treat that a little bit more in detail. Let's now start with our first experiment on the laws of reflection and refraction. Hello everybody. So this experiment is about Snell's law and of course the law of reflection. So what you see here is a laser beam that enters at 30 degrees and leaves at 30 degrees, so it is just straight propagation of light. However, now we are going to place in an optical surface that is basically indicated by this flat area here. So when I put the optical surface in here, then of course two things happen. One thing is we get a reflected beam and we get a refracted beam. And you see now that as expected, the reflected beam leaves at precisely the same angle as it enters with respect to the normal to the surface. However, the refracted beam leaves at a different angle than it enters. So this is described by Snell's law. And there's another interesting aspect on Snell's law, which predicts that when we change the input angle here, then there's a particular angle, which is about here, where we do not get any transmitted beam anymore. So here we are at what is called the critical angle, and that is at an input angle of 42 degrees for this particular material. So from both of these things, the 42 degrees angle or the exit angle when we were at 30 degrees, so if I put this back to 30 degrees, like this here, you see that we are leaving the material at 48 degrees here. So from both of this, you can work out the index of refraction of this material, as described by Snell's law. We will straight away continue with another experiment that I call the fish. Hello everybody. I want to tell you today a story about a little fish. You can see that fish right here. However, if we switch, you see now, the fish is invisible. So how comes that we cannot see the fish? Well, there's glass right here, and the glass hides the fish from the view. However, something really interesting happens when you now fill that glass with water. So you nicely see, when I filled the glass with water, the fish became visible from both sides. We saw it actually 2 or even rather 3 times, as you see here. How is that possible? Well, the reason is that the light rays that travel from the fish into this direction are then redirected into the different directions towards the camera. The same way. This way, they first travel outwards and then straight towards the camera. And of course, this is called the law of refraction, as you've seen in the previous experiment. So in this experiment, you've seen that the position of the fish or the angle at which you were seeing the fish did actually matter. Well, does that have any practical implication? Maybe not so much to us now, but it actually did a lot for people in Stone Age times. So for example, if you wanted to hunt a fish, then as shown in this picture here, you seem to be looking at the fish. You have the impression the fish is over here and you're trying to spare it to have some dinner, but in reality, the fish is here. So of course, if you train a little bit, you will learn that you have a bigger chance of hitting the fish by pointing your spear more downwards, because that's the position where it really is. And so the laws of refraction actually allow us to calculate where to point our spear when we see the fish here. So the next phenomenon I'm going to introduce is the rainbow. So this everybody has seen already. However, very few people really understand how it comes to be that we see such a thing as the rainbow. So the first thing you have to notice is typically on Earth we see a rainbow in this shape, but in reality it's not only a rainbow. It's just that the lower part of this circle is blocked. So you can really, one should speak of a rain circle. And you see that nicely if you're flying in an airplane and passing next to some cloud of rain, then you really see a round rainbow, and you see that this is really a round ring rather than just a bow. Of course, there's barely any water between our point of view, a little bit, let's say 1.5 meter above the earth or something, to the downside, because then we are hitting this here, the surface of the water, or the concrete in other places. But if you're up in the air, you can really see, you can have access to the drops in midair that cause this phenomenon. But how do they do that? Well, so how can we explain such a beautiful effect like the rainbow? Well, first of all, let's look when we see a rainbow. A rainbow can only be seen in the morning and the afternoon. What is the reason for that? Well, you have to have your sun in the back, as you see here. There's a person standing there with the sun in the back, and the light rays from the sun traveling pretty much parallel travel in this direction. And then you have water droplets in the air, and the water droplets have all kinds of effects of refraction, like shown here, and reflection. To explain the primary rainbow, you need to think of a single reflection and two refraction effects. When the ray basically enters the water droplet, it changes direction, it gets reflected at the back and changes direction again. But is that enough to explain the rainbow? Not really, because of course all the different rays that hit in different positions here would have equal probability to hit somewhere, and they would basically give you a mess of directions, and that would just mingle up the light, but white light would still mix to white light. So why do we see a rainbow? The interesting effect is that there will be an extremal position. That means when you look at all the different input rays that are parallel, that come different directions, there's only one extremal output ray direction, and that's why the light sort of concentrates at a particular direction, and we will follow that effect now in the next slide. We'll understand that better. So here's what happens. This is the anti-solar point. That means the sun is coming from the left here, pointing straight to the right. And now let's see what happens. If we point a red light in this direction, it will leave at a particular angle here. If we point it in the same direction but at a different position of our droplet, so this is the model of our droplet, it goes here and then it goes here. So what you've seen is the angle towards this normal is first increasing and then decreasing again, and this gives this extremum position, and that makes the eye perceive red light along this direction. Now interestingly, these are other rays and they're sort of all over the place, but only one extremum here. If we now take a different color, green, you see that this, because of dispersion, that means the refractive index is dependent on the color of the light, we get a tiny little bit of a different angle. So instead of 42 degrees, it is 41 degrees near the extremum. And that, of course, is then the reason that we see different colors in different positions. So you see here the same phenomenon of extremum, just at a slightly different angle because it is a slightly different refractive index. So this effect of extremal position of the perceived light we will now explore in an experiment. So this experiment demonstrates how a raindrop works, or rather how a rainbow is actually generated. So here I have two rays, a green ray and also a red ray, and I'm going to show you some interesting effect when such a light ray, you can imagine this being the sun, hits a circular drop of water. So what you see is that, of course, when we hit it, we get refraction, reflection, and another refraction. So what I want you to concentrate on is actually this ray. the ray that has been refracted, reflected, and refracted again. And interestingly, as I move in parallel this up, you see that this performs a very interesting movement. At the beginning, it moves upwards, then it seems to stop, and then it moves downwards again. And so what we do is we try to find the position where it changes its direction. So you see now, this is about it. So when I move it upwards, this is the highest possible position, and I mark it here. And now we look at the same effect when I'm using the red light ray. So again, the ray moves up and then moves down again. However, as you see, there's a different angle, which is about here, roughly 1 degree further out, where it reaches its outermost position. And this is where basically the red light coming from the sun seems to be concentrated, and as opposed to the green light. And so we would expect, when we look from here, that we see a red rainbow in this direction, and the green part of the rainbow a little bit more inside. So if you look upwards, the red would be outside and the green inside. Now we understand a little bit better how the rainbow functions. But as you might have noticed, we've actually only explained this part of a rainbow effect, so the primary rainbow. But if you have particularly good rainbowish weather, then you can see other effects. For example, a secondary rainbow, like it is seen here, where the colors are reverted. So rather than red being outside, it's now on the inside. And you can even see sometimes what is called supernumerary rainbows. So you can see another sort of red, green, blue inside, and in very rare occasions, even like twice the same effect. And there's also an effect that you see here, which is that there's a brighter area in here of brighter light and dark light between the two rainbows. So all of these effects can, of course, also be explained. This is the effect by one reflection. The secondary bow is you get by looking at two internal reflections of water droplets. And the supernumerary rainbows are explained by diffraction effects. And that is also why the quality of the rainbow depends a little bit on the weather conditions, because it depends on the size of the droplets. If the droplets are too small, then you have to consider not only ray optics, but also wave optics effects such as diffraction, and they can actually ultimately give rise to the supernumerary rainbows. So here's a little more detail on the rainbow. So these figures on the left show you what happens with two reflections. So the light enters here and you get a similar extremal effect, this time only the other way around, such that the red is inside as an extremal position, in this case at 50.4 degrees, whereas the blue light would be extremal at 53.5 degrees. So that's why it is the other way around. Okay, so enough about rainbows. So what I've done here is there's a table of refractive indices of different media. So this is sort of good to know. So in the future, when you get a little bit experience working with actual optics, you will at least remember a few of them. I would say the most important one is that vacuum, of course, has a refractive index of 1, which means that you have, for example, just the normal speed of light that is typically referred to as the speed of light in vacuum. So the refractive index doesn't change from there, of course. Then air has pretty much the same refractive index. So only in the 4th digit after the comma you get a change. However, if you have something like water, you get a pretty massive change. Like you see that the wavelengths get actually shortened by 1.3 times. So the effect of the refractive index is that it shortens the wavelength. So you divide the vacuum wavelength by n to get the wavelengths in the medium. So a factor 1.33 in water. In typical glass, it would be 1.51 BK7 glass or 1.52. And then you have other glasses. That is, of course, the whole art of constructing objectives and so on, is use different glasses to get ideally achromatic performance in the end. And diamond, for example, has a very high refractive index, but many media, for example, if you go to the IR, you get typically quite high refractive indices, for example, of silicon. So the rule of thumb is whenever you get close to an absorption possibility of the medium, you get relatively high refractive indices. So as you note here, this table is given for 20 degrees Celsius and a particular wavelength. Why? Well, because all of these depend on the wavelengths and the temperature. So that is an effect called dispersion, that the refractive index, the index of refraction, depends on the wavelength. So remember dispersion. So let's look a little bit more in detail on the effects of reflection and refraction. We start with reflection, and of course you know that the law of reflection says that the input angle towards the normal is equal to the exit angle, and you see that here, if we stand in front of a mirror hanging at the wall as shown here with a particular size, for example, the light from the tip of our shoe reaches the mirror, gets reflected, and then finally reaches our eye. However, if we look at that, we are not aware of the mirror. Our brain thinks that the light comes from this line, and it basically traces the line back in this direction, and we get what is called a virtual image here, standing there. And if the mirror is big enough, we can just about see our own feet here again. Of course, with the eyes, we would basically look ourselves into the eyes and then also perceive that at a particular distance here. So, how about curved mirrors now? What this is, it indicates a curved reflective surface. So in this case, a concave mirror. So now we have an object somewhere, and we are looking where an image will be formed. And in this situation, if the object stands inside this curved mirror, relatively close to it, you see that the laws of reflection would predict that a ray this way, input angles, output angle to the normal goes this direction. And here, for example, if the ray that goes from the top of the object to that sort of point where the optic axis hits the mirror, then it would just leave at the same angle outside. And so you see that these rays never cross, therefore we do not get a real image of the object. However, if we then would place our eye here, we would perceive an image here. It would look to us as if there's a focused enlarged object here. So we get an upright virtual image of the object here. Note that this curve here has a focus position that is here. What does that mean? That means that a parallel rays here will actually focus at this point here, which is half the distance to its actually radius. So if we had this position is basically the radius of the curve of this circular approximated curve here. And if you had a ray that goes from here towards the mirror, it would always return to itself. So that is why it's called the center of curvature here. So that's an interesting effect, that curved mirrors always have sort of a center of curvature and a focus, and they are different in distance by a factor of 2. So if we now move the object to a different position, we actually see that this graph here doesn't show an object. What is the reason? Because if the object is just at the focus position, well, it would be infinitely big at infinite distance. You see that these are two parallel rays now, and you see that the rays never cross, neither on this side to form a real image, nor on this side to form a virtual image. So that is an image at infinite distance. Is that a real problem? Not really, because if we place our eyes here, we would nicely see such an image at infinite distance, because for all practical purposes, if we look at the horizon, or the clouds or something like that, that is infinitely away for practical purposes for the eye. So we don't have a problem seeing these images at infinite distance, but how big is it? Well, it's infinitely big because it's infinitely far away, right? So that doesn't make sense. And for this, the reason in these situations, usually you refer to a particular distance to measure the size there when you talk about magnification. And so this is basically a particular distance that is sort of close to the close point of the eye. So I don't remember exactly that distance, but it's in the range. It's, I think, less than a meter for sure. So if we move the object further away, you see that we now get a real image that is upside down. So an inverted real image, and it's magnified here. And then we move the object even further away. At 2f, we just get with the 1 magnification an inverted image. That means that the light rays here are crossing here and they form an image. We could actually put a screen here, and on the screen we would see a nice image of a, for example, self-luminous object. If we move it even further away, then we get a demagnified image that is real and inverted, like you see here. So of course there's not only concave mirrors, but there's also convex mirrors, as you see here. So in this case, we would get a demagnified virtual image on the other side of the mirror. And you can see a nice example of that. Here is such a curved mirror, which gives us a nice overview around the corner, so to say, if there's something. So you see these sort of mirrors often in traffic as traffic mirrors to basically indicate what's going on in a bigger field of view. Well, I want to also mention what is called the parabolic mirror, because that is in a way an ideal system to focus from infinity to the focus point. So imagine that we have light from infinite away. Stars could be such an example, and they would perfectly focus here to the focal point. Well, where do we need this? For example, in a satellite dish, we want to really capture the signal of the satellite with maximum power, and we want to therefore concentrate it as good as possible on our detector, and that's why such a parabolic form is used. However, in optics, you have to be a little bit careful, because this looks all fine for this particular situation. However, if we had now an infinite distance at some angle, we would find that the focus is not quite as good anymore. So we have only a certain sort of field of view, in other words, a certain range of angles where the image quality is acceptable. Here you see that whole thing rendered in 3D, and you can see and appreciate that all parallel rays on the whole surface of the mirror would really focus in this focus. One other way of looking at that is that they also constructively interfere here. When we come to wave optics later, we will follow what is called Fermat's principle, which means that we have to ensure that not only do they all meet in the same point, but they actually have the same path length. So if you add it up mathematically, which is sort of a fun exercise to do, the blue lines for each of these paths, you would find that they are the same length, and that of course defines the shape of the parabola that you see here. So what about reflection when the surface is not that well defined? And you have here an example of a rough surface, and what you see is that of course we get reflected rays that go in all directions. That depends on where they locally hit the surface normal, how it is oriented. And depending on the roughness, you get a different distribution of scattered light. So you call this scattered light from the surface. And under certain conditions, this distribution follows what is called Lambert's cosine law. So you can basically say that the power here follows a particular distribution, which is called Lambert's cosine law. Of course, you do have also a specular reflection, which is sort of, if you take the surface normal on a coarse coordinate, the specular reflection would follow the normal laws of reflection at such a surface. However, the micro orientations are different, and that give rise to this what is called scattered light or diffuse reflection. As we've now talked a little bit about mirrors, I want you to think about this question. Why does a mirror reverse left and right, however it does not reverse the up and down direction? So what is so special about left and right, but not at up and down? If you look at a mirror and you raise your right hand, the person in the mirror clearly raises his or her left hand, whereas you've never seen in a mirror yourself upside down, at least not with a single reflection. So why does the mirror reverse left and right, but not up and down? Think about it and then tell me the answer. So we are going to continue with another effect that has to do with reflection, but a very special kind of reflection that's called total internal reflection. Well, look at the experiment. Here I have a rod of glass, which is a model for an optical fiber. So what you see is if I put it into the beam, of course the beam goes straight through. But now the interesting thing is that with an optical fiber or rod of glass, if I go in at a certain angle, you see that the light gets reflected by total internal reflection at not only one, but two or even more points, and it gets guided into this rod, in this rod of glass. And if you imagine now this was a kilometer long, it could still guide the light perfectly as long as we stay under the critical angle for total internal reflection. So this is a model of a glass fiber. As you can see, a laser goes into the fiber and follows the bend, comes out here. Of course, the fact that you see green light everywhere is because it is a bad quality fiber, and so it scatters everywhere and that light goes out to you. Now the interesting part is, well, you see the light comes out of the fiber, but now we're going to fill this bassin here with immersion oil, and that leads to a phenomenon that is called frustrated internal reflection. So the normal internal reflection that's happening everywhere in this glass fiber cannot happen anymore, and the light goes straight out into the medium, and therefore you should watch here and see that there's no more transmission of this glass fiber. So you see how there's no more light transmitted through the glass fiber right here, because it all leaves here. You can even see a little bit of green light on the block here. So now that you've seen what total internal reflection is, let's look at the explanation. Well, imagine we have water and a surface between water and air. And now we have a light source underwater and we send it towards the other direction. Well, the laws of refraction now tell you that there's two rays, of course the reflected ray and the refracted ray, and the refracted ray leaves at a particular angle. And when you go from the optically dense medium, i.e. water, into the not so dense medium air with a refractive index close to 1, then we get a bending away from the normal. And now the funny thing is, according to Snell's law, that there is one particular situation where the exit angle would be at 90 degrees from the normal. And then we have the trouble if we go at a ray that is even bigger than that. So this angle is called the critical angle. If we go beyond the critical angle, like you see here, when we have trouble, because there's no, according to Snell's law, there's no solution to the problem of a refracted ray. It cannot go anywhere. It cannot go beyond 90 degrees, because then the sine of that angle would even go smaller again. So there's simply no solution. Well, or more precisely, you would get a complex valued solution, but that, of course, doesn't seem to make sense at first. And so the effect then is that all the light, all the energy of the light has to go into the reflected ray. So therefore we get what is called total internal reflection. Internal because we stay in that medium, that optically denser medium. And of course that's a very interesting and very important effect in practical optics. So where is it used, for example? Well, as you see here, it is used as total internal reflection in prisms to simply have a mirror of very high quality, because total internal reflection has very close to 100% efficiency if the optical surface is very flat, and so you're not losing any energy. And so this way you can redirect light, and that is used, for example, with what is called poro prisms in binoculars, and this allows you to displace the incoming rays from a point here to a point here, so that it allows you to have two effects. First of them, the first effect is you can actually tilt them with respect to each other, which allows you to control that distance, that allows you to set the interocular distance in such a binoculars. And the other thing is also it increases the distance of viewing, and therefore increases depth perception when you're looking at the scene through such a binocular. So here you see how binoculars look like. This is a very old example of binocular by Ernst Abbe, who lived 1840 to 1905. And you see the poro prisms are actually here and here. So it works like this. There's such a poro prism which bend the right ray twice, and here twice again. It goes this direction. And then by changing this angle here, you can change this distance, which allows you to adjust the binoculars to your preferred distance between your eyes. So let's look at such a pair of poro prisms in the experiment. Now let's look at some applications of total internal reflection. Of course, the most prominent application that you all probably know is guiding light in fibers. So all our telecommunication is basically based on these fiber optics, where they use infrared light that is guided by fibers. How do they work? Well, they have a core, like you see here, and what is called a cladding and a coating. The coating is protecting the fibers from being damaged. The cladding is a different material that has a lower refractive index than the core material. So this way we get a little bit of a difference in refractive index between core and cladding, coming from the dense medium towards the optically thinner medium. And now we have total internal reflection. Of course, not at such a high angle typically as it is shown here, but typically at a relatively low angle, and then we can guide the light. And the quality of the material nowadays is so great that you can basically guide it for many, many, many kilometers without a loss in light intensity, and you get millions of reflection and not lose the energy. So inside that fiber, it looks like this. Essentially, you're going this way and this way and this way, and you continue like this. So if you go to the wave optical model, you will have to refine this a little bit, and there's different types of fiber depending on the size of this core material. If it is small enough, it is just big enough to guide one, what is called mode of the light. So an electric field distribution that just has sort of one maximum and goes down again, and that stays like this, and then it basically alters this idea a little bit. You would then say you have everywhere these reflections all the time, right? We will now continue with a number of experiments, starting from a curved glass rod that can conduct light, similar to a fiber. So it's a model of a glass fiber, which then stops conducting light when we dip it in oil. Then from there we continue into multiple fibers that show you how this can be used for imaging, first in a model and finally in a really image conducting endoscope, so that you can see how you can transfer an image from one position to another one with such a device.
this is a model of one part of binoculars. So you see the light from the world at a large distance comes here. First lens collimates it, or rather starts to focus it. And then these two prisms are called prisms. And you see that the light goes this way, once around, and then goes to the eye. And so the typical sort of imaging system is formed by the three lenses, but the prisms serve to change the distance between from where the light comes here and where the eye is. And this allows you to have a larger parallax. So if you had the other part of the binocular, it would be sitting on this side. And now the interesting part is you can also change the distance between these two lines without affecting the position of the image, so to say. So you can watch, you can change this way. You can modify the relative distance to the eyes, because this is what is kept constant, the distance between the outermost incoming beams. So you've learned how a binocular functions. So here you can see how total internal reflection can really allow you to guide the light in a totally flexible way. What I have here is a model of a optical fiber cable, if you want, and also a model of an endoscope. So there's lots of small fibers, and each of them conducts the image to this side. You can see that here. If I put light into these fibers, you can see sort of how it follows along. And we're going to see in the next model how this can be used to transfer an image from one side to another side in an endoscope. So this is the model of a fiber-based endoscope. So you see that an image signal that is here, for example, something inside the body, gets transmitted through all these many glass fibers that are nicely sorted, such that on this end surface of this fiber bundle, the image appears. And if we now zoom into this, you see an image of the emblem of the university that you see there, which is, of course, originally a printout that has been put here. And what I'm going to do now is I'm going to move this left and right, and you might notice the changes. And if we zoom in again, you see how this image now moves. So you've learned how an endoscope works.
So there's another effect called frustrated internal reflection, in which case now we don't have just a liquid medium that we can bring into the vicinity of the total internal reflection surface, but we have a second sort of medium with a high refractive index that is solid that we bring close to it. And now interestingly, there's a wave optical effect. If it comes close enough, we can still get this effect of transmission. So precisely speaking, this doesn't need to be the distance 0 as it is shown here, where of course the light will just travel straight, but it can be a tiny little gap that is sort of on the order of the range of the wavelength. Then we can get still light going here. So for those who have heard quantum mechanics before, you might know this effect as the tunnel effect in quantum mechanics. And in optics, we speak of what is called the evanescent wave, which sort of forms as a bound optical wave, if you want, to the surface, and it probes a little bit the space outside here, and if there's something else there, it can then go into that medium and a part of it can go through. So we will demonstrate this with the next experiments, but to make it big enough for you to see this effect, we actually do it with microwaves rather than with optical waves. So this is total internal reflection. with frustration based on microwaves.
Here we have an experiment on total internal reflection. You see here microwaves in the centimeter range being generated by this klystron. They are reflected, total internal reflection at this surface. So this is working like a glass prism, but just for microwaves. It's made out of paraffin or something alike. Gets reflected, and this is our detector. And then the detection goes to a loudspeaker so that we can hear the sound as you might hear now. So now what I'm going to do is I'm going to put a second piece of glass, and when I approach the first piece of glass, or rather paraffin, you see that I have deleted the total internal reflection. Now the microwaves pass right through, and when I then open it again, you hear again this sound. Of course, the sound is just an amplitude modulation of the microwaves, but what is really detected are the microwaves. Okay.
Can we use this effect to something good? Well, yes. This is actually how fingerprint sensors work. So you see here a model of a fingerprint sensor. We have a glass prism, we have total internal reflection with more or less parallel light hitting the prism. And in this case, we're imaging the backside of the prism here onto a CCD camera. And now when we put our finger against it and we press it slightly against it, we are going in the distance below this one wavelength distance, but not everywhere, just at the points where our finger ridges of the fingertip sort of are pointing out, and then they touch this glass prism, and that's why we can get a fairly nice image of a fingerprint by such a device. And of course, everybody has seen this when you travel, then they record your fingerprint exactly with such a device, a total internal reflection based device, and it might then look something like this. And of course, this is also how the mobile phone sensors work with fingerprint devices. And interestingly, I show this because this is kind of a fun story. So the Chaos Computer Club in Hamburg actually they showed once that this idea of safety with fingerprint devices is really not necessarily a good idea. And there was a famous minister, Wolfgang Schäuble, that was sort of talking about how safe this is, and they used this and they collected a wine glass or something like this from him and then copied his fingerprint device and gave it pretty much to everybody to have such a stamp with Wolfgang Schäuble's fingerprint in some rubber printed so that you can use it to unlock his bank account or something like this. So this was of course a publicity stunt to show that this is really not safe and how easy it is, comparably easy it is to copy something like this. So now we're going to show an experiment with fingerprint as well. In this experiment, you will see how a fingerprint device really works. And in this case, we don't use a camera. We directly project it to a big screen with a powerful lamp.
Here we have another example of total internal reflection. The light from the light source is collimated, and then this prism on the rear side of the prism, it is total internally reflected and then directed into this direction onto our screen. However, the specialty here is that this objective images the position of total internal reflection to the screen. So what we are going to do now is I press my finger against this glass plane, which will frustrate the total internal reflection. So at these positions where my finger touches the glass, total internal reflection will be prevented, and therefore we don't see anything on the screen, or rather we see a black spot on the screen. So what you see now, if I touch here, is very nicely on the screen, you see my fingerprint. Okay. So Here you nicely see my fingerprint. And as you see, the fingerprint even stays when I've gone, because there's still a little bit of residual fat left on the glass, which frustrates the total internal reflection, and so you see black stripes there. This is how fingerprint sensors actually work when you go to the border control, for example.
So now that we've seen the basics of geometrical optics, we will continue with a very important but slightly intricate principle called Fermat's principle. So to explain Fermat's principle, it's useful to first look at a sentence that Heron of Alexandria once said, that says light takes the shortest path. And that, of course, can explain reflection. However, there was Pierre de Fermat who then made this more precise by stating that light travels the path between two given points, which requires the shortest time relative to the neighboring path. So time means the time of propagation that light takes. So let's look at this a little bit more in detail, and how we can use it to explain optical phenomena with it. It can actually explain reflection and refraction at the same time, given that light travels slower in an optically dense medium. This is a picture of Pierre de Fermat. So this is a graphical picture that shows you what is meant by that statement. It means out of all the possible ways, so if light could travel this way and this way and this way, it takes the shortest path. And of course, in a homogeneous medium, that would simply mean connect the 2 points here by a straight line. And that sort of explains why light seems to travel along a straight line. And of course, that forms the basis of geometrical optics. So light always follows an extreme path, either one that minimizes the time taken or one that maximizes it. So there's a mathematical version of Fermat's principle, which is based on variational calculus. For those who know how this works, you would calculate the first variation of the optical path length, which is defined by this integral along the position S over the refractive index. So that's the total optical path. If you go from point 1 to point 2, that this one needs to be 0, and that would explain how the light actually seems to travel. So let me see if I can draw an example for you on this slide here. So imagine that you have a surface, an optical surface here, and we have a light source here, and we have a detector here. If we now want to know where would we see, if we look basically in this direction from this side here, where would we see that light source? How can we work that out? Well, we could, for example, put the knowledge in that in a homogeneous medium, let's say this is one medium N1, and this is another medium N2, and in a homogeneous medium, it would travel on a straight line. And so that means we really just need to look at all the different paths that would be connected by straight lines. And so, for example, one such different path would go from here to here. We could also draw another path, maybe this way, or we could make another path this way. The question is, which path does the light take? And of course, the answer is it would take the one that minimizes this sort of integral here. And that means that we have to calculate the distance here to a particular point here. So that would be distance as 1 and the distance as 2. And we would have to calculate the optical path by looking at refractive index 1 times S1 plus the refractive index N2 plus times S2. So this is the optical path in medium 1 and the optical path in medium 2. We add them together. That is often indicated as optical path difference. So this optical path as a sum, we would then want to minimize. So it takes, the light takes basically the shortest path when we add the two together. And actually, this is analogous to a situation that works like this. So imagine you are here and you want to get to this position. Why? Because let's say this here, N1 is the beach and N2 is the water, and you want to rescue a swimmer there. So the question is, what do? Do you run straight to the shoreline and then swim the rest? But that would have the advantage, the disadvantage that you would have to swim quite a lot, and you can run a lot faster. So you could also, for example, run to some point somewhere here, so that the distance to swimming is the shortest. But then, of course, the question is, what is the best to do? And the best is also to minimize the optical path, because that takes the shortest time to get from here to here. So if you really go through the math and work all of this out, surprise, surprise, what you will get is actually Snell's law just explained. So now we are going to deal with geometric optical imaging by a few examples. So the first rule is all light rays from one object points unite in a single image point. Of course, that's only true for optics that forms images, but if you talk about lenses, that's what they're meant to do. And this is the way we work out where the image is and how big it is. So you call this point-like imaging. And the image should be geometrically similar to the object. Of course, that's also a condition so that you can define that as imaging. That means a line should become a line and a plane should become a plane. So this is called Gaussian imaging if you fulfill these conditions. So here is an example, a simple example. If you try to work out what happens in terms of ray optics when you have an object, as seen here on the left side, and this is image to an image position, and this in a way is the simplest case. Here we have just a single optical surface that is sort of given by this surface, where we go from one medium with index n to a medium with index n prime. And you see here that we can draw certain rays that are important. One ray is the one that let me change to a pointer again. So you can nicely see this point here where the light ray goes straight on the optical surface, and therefore it doesn't change direction at all. And so in this case, if we have a spherical surface as indicated here, it would be the ray that goes right through the center point, and this way it can continue straight. And another important ray is the one that crosses the optical axis, and in this case we would apply Snell's law here, which would be n1 times sine 1 is n2 times sine 2. So you would get this angle and work out where this image point is. And so this is a really important condition, and it's part of the exercises to actually work out really the mathematical equation where this image.
So this experiment is an example of a lens. So what you see here is a single optical surface formed to a circle, and of course a straight light ray hitting it right at the apex is going to make it right through. However, if we now go to a different position, for example, by moving it up and down, you see that it gets a different angle, as described by Snell's law. Now, the interesting bit is that no matter how much I move this up and down, there's a particular position somewhere close to the end surface where all these rays focus. And of course, that's what you can see. If I now put 3 rays simultaneously in, you see a reasonable focus right here. So this is described by the lens maker equation, where this focus is to be expected in such a material. There's another interesting effect you can see if I go to a higher angle ray. So if we now mark the focus, which is roughly here, you see now for these high angle rays, the focus has shifted slightly to a different position. So this is an effect of what is called spherical aberration, which you get if you're going with high angles in a curved surface optical material.
So in this example, I'm going to show you how to make a construction to see where an image of a particular object forms. So for this, we put an object somewhere, and now the task is to work out where the image will be forming. For this, there's basically three different rays that we have to consider. The first one, really important, is a ray that is parallel to the optical axis. So you see here the optical axis right through the center of the lens, and this ray originates at the top of this arrow representing the object, and it is parallel to the optical axis. And any ray that is parallel to the optical axis, by the definition of a thin lens, has to run through the focus, through the back focal plane focus point on the optical axis. So that means we have to draw the ray like this, leaving the lens. So of course, this doesn't tell us yet where an image of the object will be formed. So for that, we need a second ray. For example, we can draw another ray that goes through the front focal point on the optical axis of that lens, and then hits the lens, and it will continue now as a parallel ray to the optical axis. So if we continue that ray, now the image will be formed. So there's a third ray that we can draw, and it will also give us the same image point here, which is the ray right through the center of this thin lens. So this ray also crosses here, and then altogether the object image will be formed here, which is a real image that is inverted in direction, and in this case a little bit demagnified. So please remember, there's three really important rays. The parallel ray to the optical axis goes through the focal point, becomes a focal ray becomes a parallel ray, and what is called the principal ray right through the middle of the lens stays like it is and just continues. So this is the rules for thin lenses. We will see a little bit later how to expand this set of rules to thick lenses. Here is the image being formed now.
This little experiment on refraction is actually quite interesting, and this time I am not going to tell you how it really works. So what you see here is a round bowl of water. Well, at the moment, no water in it, and behind it, all these arrows. And as you see, the arrows are nicely pointing from left to right. However, look what happens when I fill this bowl with water. So now the arrows, instead of pointing from left to right, are pointing from right to left. Think about it. What has refraction to do with the direction of the arrows?
So let's look at other conditions. For example, if we have our object between the focal point and the lens, let's draw the rays. Parallel ray goes through focus, diagonal ray keeps going on. So you see already now they don't cross here. So the only way to make them cross would be somewhere there. And indeed, what we need to do is we draw this dotted line as tracing back the rays, and then we get this image, and this is called then a virtual image, because you couldn't put a screen there. There would be no light. It would be just going this way. However, if we put our eye here, we would perceive an image being at this position there. So this is, in this case, an upright image, and it's virtual because we need the dotted line. So basically, whenever you need the dotted lines, meaning tracing back rays from where they seem to be coming, then this is a virtual image. So let's look at other lenses that are not convex but concave lenses. So this is a biconcave lens, which means it has two concave surfaces. And for example, we have an object that would be further away than the front focal point. And now you have to imagine that this ray will continue this way. Why? Sorry, because it now we've inverted the focal point. So rather than trying to draw through here, we have to now say, well, it will basically bend the light in the other direction. It will seem as it comes from this focal point. So you can draw a dotted line from here, and that is how you construct this ray. The rule for the straight rays through the middle always applies, and if I go so if you then look what you have this exit ray and this exit ray. If we trace the rays back, you see now that we get a virtual image, and it's inside, so it's upright and demagnified. So it's a virtual upright image in the case of biconcave. So if we put our object closer than the focal distance, let's work out what happens there. We have this ray again, parallel ray seems to be coming from the point F, and the diagonal ray goes straight through. And again, if we connect the two rays, we get also a virtual upright image inside. And this way you can then work out what really happens. And there's of course converging lenses that work like this, and you have the convex lenses and the concave lenses that are diverging lenses. So here you see sort of an animation what happens. So you see that we go from a real image in this case to a virtual image this way, and at the focal point we have well, neither a real nor a virtual image, because both the rays don't cross, but we have an image at infinity. That's why I would call that a virtual image at infinity. If you placed your eye here, you would still be able nicely to see that image actually. And that's how most of the systems actually work. You focus to infinity when you observe your image with the eye. And here you have a similar diagram, what happens for diverging lenses. And you see in this case, we really just have a virtual image where the magnification changes a little bit. Our next experiment is actually whiteboard optics, which is a nice way to show you directly what happens to the light rays by some sort of laser pointers.
This is a model of one part of binoculars. So you see the light from the world at a large distance comes here. First lens collimates it, or rather starts to focus it. And then these two prisms are called prisms. And you see that the light goes this way, once around, and then goes to the eye. And so the typical sort of imaging system is formed by the three lenses, but the prisms serve to change the distance between from where the light comes here and where the eye is. And this allows you to have a larger parallax. So if you had the other part of the binocular, it would be sitting on this side. And now the interesting part is you can also change the distance between these two lines without affecting the position of the image, so to say. So you can watch, you can change this way. You can modify the relative distance to the eyes, because this is what is kept constant, the distance between the outermost incoming beams. So you've learned how a binocular functions.
So what about the rules with mirrors? So we have a concave mirror here. If we have an object closer than the focal point, you've already seen before that there's this focal point and the center point, which is twice the distance of the focal point. So a parallel ray would go straight through the focal point. So that's again the same rules. Parallel goes through focus, and a point coming from the center would be directed back to the center. And this way you can work out what happens. Well, and another thing is also a ray that seems to be coming from the focus, which would be this direction, of course becomes a parallel ray like this. And all three rays give you a virtual position here, which would predict an upright virtual image behind the concave mirror. Like this, virtual upright. We have a convex mirror. We put an object, for example, here. What are the rules there? We have a parallel ray. It will be reflected as if it was coming from the focal point here. So we have to draw it like this. If we have a ray that is directed towards the center, it would be reflected back in its original direction. And if we have a ray that is directed towards the focal point, it will be reflected parallel to the optic axis, to the optical axis, like this. So we get a virtual image and it's upright here. So what about thick lenses? In the case of thick lenses, we have to be a little bit careful because now we have two planes at which we have to apply the law, Snell's law, basically. And so how do we construct this? Well, we can replace that lens with a virtual surface like this here, which is called the principal plane, at which we simply pretend there was a thin lens. And so this would be the front focal distance to what is called the first principal plane here. So front side first principal plane, at which a ray from the focus would seem to be bent. If we basically look from here backwards, it looks like this is the bending position. This is how this is worked out. And then if we have a parallel ray that focuses to a point here, we can also define another principal plane at which this bending seems to be happening, and we get the back-sided focal distance here, and this is the second principal plane at which parallel planes seem to be bent. And so now we have two different rules for parallel beam that focus to another focal point. Well, on the other side, at a different plane, that's the main point, compared to the ones that come from focus. So we need now these two principal planes to draw what happens in thick lenses. So here's an example. If we want to work out where the image with a thick lens is formed, we take the parallel beam going to the second principal plane, we let it go through the focus here, as we've just learned, whereas the beam here that goes through the front focal plane goes to the first principal plane and then becomes parallel. So this is where our image formed. So what do we do now with the diagonal beam that previously didn't do anything? Well, now there's a new rule. We have to sort of teleport it from the first principal plane to the second principal plane and then continue parallel to the original direction. and it will then also cross in this position. So here's our image. Of course, similar to a thin lens, it's an inverted real image that we have here.
So here I have a parallel slab of glass. What I do now is, if I put this into the beam, of course, as you probably expected, nothing much is going to happen. The light is going to go right straight through. However, the question is, what happens when I now tilt this? Interestingly, you will see that when we get some tilt, this beam seems to move. However, it does not change the angle. So as you see here, because of Snell's laws, you simply get a beam displacement introduced by this parallel slab of glass. So this is actually a very nice way. If you want to move an image ever so slightly, you just put a plate of glass and you rotate it, and then you can get a very, very fine control of a beam displacement. This is even used technically in some instruments.
So the part about aperture stops and pupils and windows, I will not